Okay, lesson 30. We are graphing. We are really looking at, it says graphs of tangent. Really, we're just kind of reviewing all of our trig function graphs. Okay, we did a lot with sine and cosine last year in pre-cal. Okay, so we know a lot about those. And we looked at secant, cosecant, tangent, cotangent. So we're going to look at those, put it all together, look at some relationships. So, first two up here, do those look familiar? Y equals sine x, y equals cosine x. You've got one cycle of each showing, right? A cycle goes from 0 to 2 pi. Remember with sine, you start at 0, 0. You max out above pi over 2. You cut through pi. You bottom out at 3 pi over 2. And you end back at 2 pi, right? With cosine, you just start in a different location. It's the same graph, but you're starting up here at 0, 1. And again, every fourth of the way, we cut through, we bottom out, we cut through, we max out. Okay, however you remember it, I don't know. Now, tangent. I'll be honest, sine and cosine I can remember pretty easily. Tangent, I always have to stop and think a little bit. Do you guys remember the basic gist of what tangent looks like? Okay. Tangent to me is, y equals x cubed. How it's that? It's a bunch of those. Okay, it's a bunch of those y equals x cubed separated by asymptotes. Now, the key is, how big are those curves, what they look like y equals x cubed parts? Where are their zeros, and where are the reciprocals? Okay, and those are the pieces I look at here. Now, if I say tangent as a fraction, what do you guys know about tangent? It's sine over cosine, yes? So that is a connection that I'm going to use here. Is the fact that tangent is the same thing as sine divided by cosine. And the reason I say this is because an easy way to remember is, since sine is on top, any place that sine equals 0 is where tangent equals 0. So what do I mean by that? Any place sine equals 0, tangent equals 0. Yeah, they're going to have the same x-intercepts, right? The same zeros. Now, cosine's in the denominator. Is cosine allowed to equal 0? No, denominators cannot equal 0. Thus, cosine cannot equal 0. Any place cosine would normally equal 0 is now going to be an asymptote. Does this sound familiar at all? I can't remember how I taught tangent last year. I feel like maybe I taught it this way, but it's been a while. So, first of all, I'm going to set up my labels the same as the previous graphs, so that we have pi over 2, pi, 3 pi over 2, and 2 pi. And then you still need officially, a 1 and a negative 1. So any place sine equals 0, because it's the numerator, tangent equals 0. So where does that mean I'm going to have zeros at? 0, pi, and 2 pi are going to be the x-intercepts, the zeros, right? And we could keep going on, right? If I say 0 pi, 2 pi, 3 pi, 4 pi, so on and so forth. Any place cosine would normally be 0, those are now going to be what? Asymptotes. So if cosine has zeros at pi over 2 and 3 pi over 2, these are asymptotes now. Okay? And then, as I said, it's that squiggle kind of in between. So if I draw my middle one here, looks something like that. I feel like mine's a little lopsided. Draw mine in on either side here. Tangent sound familiar? If we talk a little bit more about tangent, we can talk about instead of tangent having a cycle that is 2 pi, how long does it take for a cycle of tangent? It takes pi, right? Because here if you go from pi over 2 to 3 pi over 2, that's one phase or one cycle, and that takes pi. So difference is a cycle is only pi instead of 2 pi. Okay, you know how to draw tangent now? I forget, do we draw a cotangent later in this lesson or not? No?
Yes.
Yes, we do. Okay, so I won't talk about that yet. We'll get there here in a moment. Okay, moving along then to the bottom one. Do you guys remember anything about how cosecant works? Use the graph of sine x to graph y equals cosecant x. What do you guys mean? Flip it. No. It's not just a reflection. Huh? No, it's not a reflection of any sort. Okay. Let me ask you this to get us started. How are sine and cosecant related? So if I say cosecant x, it's equal to 1 over sine x. Does that sound familiar? They are reciprocals of each other. And what does this mean? Sine is in the denominator. Any place that sine would normally equal 0 is now going to be an asymptote. So right here, we have 3 zeros of sine, 3 x-intercepts at 0, pi, and 2 pi. So those are now asymptotes. So we'll have an asymptote at 0, an asymptote at pi, an asymptote at 2 pi. Do you remember what the graph does between these asymptotes?
Oh, it touches the top of the peak, and it goes back.
We kind of talked about it's kind of like taking this upside down parabola piece right here. If it was like this, it's now going to flip up.
But not over the axis.
But not over the axis. It's going to stay in between the asymptotes. So like this max right here is now a minimum. We did this last year. I know we did.
Yeah, it's just
Been a while. And so the minimum under 3 pi over 2 is now a maximum.
I feel like this was the unit from last year that we never ended up testing on. Wasn't it?
We did not. This is part of chapter 4 in the pre-cal books, if I recall. But I did end up skipping the test over it.
That's what
So that could be part of the problem of why I just ran crazy behind last year in pre-cal. That's just.
yeah, I remember our final for the first semester was pretty short.
Okay. Does that sound a little familiar now, though? I mean, you see how it works. We can still use the fact that the sine is in the denominator. So any place sine would normally equal 0, those are now asymptotes. And then I think of it as like flipping the parabolas. They're not really parabolas, but, you know. Okay, you ready for the next one? Use the graphs of y equals cosine, y equals tangent to sketch the graphs of secant and cotangent. Okay, so right here, we're going to sketch secant. What do you know about secant? What is the relationship between secant and cosine? Yeah. Secant x is equal to 1 over cosine x. So cosine's already sketched in for you. Any place cosine would normally equal 0, that is now an asymptote. So we have an asymptote at pi over 2 and 3 pi over 2? What happens between those asymptotes? Yeah. Parabolas flip, mins become maxes, maxes become mins. Sorry, I don't have much room for the middle one there, but I don't know if you guys remember when we graphed these, I said minimum requirement was to have the equivalence of 2 parabolas when you're doing a cycle. So we have the 1 parabola in the middle, and then we have the 2 half parabolas. Could you draw the rest of those parabolas? You can. Okay. Now, officially it says to draw tangent, they want us to use the cotangent graph. What is the relationship between, that's not what I wanted to write, cotangent there. What is the relationship between tangent and cotangent? Yeah. Cotangent is 1 over tangent, right? So that's what they're wanting us to think there, is that cotangent is 1 over tangent. However, what's the other way you could also think? Yeah. Cotangent x is cosine x over sine x. If we go based on the idea that cotangent is 1 over tangent, any place that tangent was a 0 is now an asymptote. So that means we now have asymptotes at 0 and pi. That part doesn't really tell us a whole lot more than that. Notice the zeros of sine, because when sine would equal 0, these are asymptotes now. Cosine is going to provide your actual zeros. The zeros of cosine are the zeros of cotangent. Or where are these zeros? They are halfway in between, right? So what were your asymptotes are now your, zeros. And do you remember the other part that changes from tangent to cotangent? The direction of the curve changes. So I think of tangent as an increasing curve because you start low and you draw up. Here it's a decreasing curve because you're going to start high and go low. Does that make sense? So now I'll be honest, I need to draw it. I need to start low. Does that make sense? So I did my middle there in between 0 and pi. So it starts up at 0, cuts through pi over 2, goes down along pi. And officially, you at least need to draw half of the other sets in, right? I don't.
So many lines on mine. I'm drawing with pencil, so it all looks the same.
It all looks the same, yeah. That is the one. Drawing tangent over or cotangent over tangent does look bad. I agree.
My graphs are looking very good today.
Enjoy it while you can, right?
You're right.
Enjoy it while it
My
lasts.
graph is messed up yet.
Okay, move along. So, graph y equals cosecant of theta plus 45 degrees. So we've got to graph cosecant, and then what do we got to do with cosecant? Shift it. Which way? Left. And what is left 45 degrees equivalent to? Okay. So left pi over 4. I know normally we prefer to think degrees, and you are welcome to think degrees. However, how do we normally label these graphs? In radians. So Now, what's the other thing? What did we know about cosecant? Cosecant is the reciprocal of which one? Sine. So there's the information that I can come up with we need to know. Let's start labeling our axis. I'm going to do my typical, go most of the way out and label 2 pi. I'm going to center this so you guys can see this. So I won't go all the way out, but you guys remember how I label? If I label 2 pi, then I will do my halves. Halfway from 0 to pi is, halfway from 0 to 2 pi is pi, and then what are the halves of those portions? Pi over 2 and 3 pi over 2. Do we have enough labels? Based on the fact that we have to shift a pi over 4, where is pi over 4? Yeah, so should we probably have those labels in there? Or even if you don't label them, can you at least put the tick marks in? Okay, I'm not going to say you would have to necessarily label, but right there, by putting that in, even if you don't tell me that's pi over 4, in my mind, I'm going to assume you intended it as pi over 4 and go from there. Now, if I'm going to put a mark halfway in between 0 and pi over 2, I need to be consistent, right? Put in all of them. Between 1 pi over 2 and pi, this is 3/4, so 3 pi over 4, because we're labeling fourths, right? Pi is 4 pi over 4, so this next one is 5/4. 3 halves is 6/4, and my next blank is 7/4, and 2 pi is 8/4. Do you see how I count in fourths? Now, based on the fact that we're going to have to go left, what else should I probably do? Make a mark equivalently left. Okay. Cosecant is based on the graph of sine. Oh, I never put my 1 and -1 in, did I? Here's my 1. Here's my -1. I would have had to put them in eventually. If it helps, could you lightly put in the graph of sine? If I lightly put in the graph of sine, what's sine look like? Starts at 0, 0, goes up over pi over 2, cuts through pi, goes down below 3 pi over 2, comes up through 2 pi. Yes? If you don't need that, that's fine. But that's just fine. Now, what do I need to do with this sine graph? Move it left. So if I move it left, pi over 4, every mark we made needs to move left pi over 4. So instead of starting at 0, 0, I'm going to start at negative pi over 4. Instead of maxing out above pi over 2, where am I going to max out about? Pi over 4. Instead of cutting through pi, I'm going to cut through the mark before it, which is 3 pi over 4. Instead of being below 3 pi over 2, 5 pi over 4. Instead of cutting through 2 pi, 7 pi over 4. I like to put those little marks in. I don't know if it helps you guys or not, but that I can't just draw this in. I have to have a teaching technique. That's my teaching technique. So now, so I only drew it dashed because, is it actually sine we're graphing? No. We're going to graph what? Not sine, but the reciprocal, which is cosecant. So what do I do now? Okay. So These zeros here are now asymptotes. So I have an asymptote at negative pi over 4, at 3 pi over 4, and at 7 pi over 4. My asymptotes do not look evenly spaced, but it is what it is. And what do we do in between those asymptotes? Flip the graph. So it looks something like that. Okay, got it? It did, but she should be in class right now, so. Because she eats our lunch, so that's what I was thinking too, so I don't know.
Maybe she's printing something out of
Okay, guys, sample 4, you ready? I can still get you some work time. We can do this. Okay, what can you tell me about secant of theta minus 20?
Right 20.
Okay. Okay, right 20 degrees, and it is the reciprocal of cosine. Yeah. The one thing here is, though, 20 degrees, does that convert nicely to radians? No. So, honestly, I'm going to leave it in terms of degrees, and we're going to mess with degrees. It's not my favorite, but it's not going to move nicely. So normally, I like working in the quarters, the halves, so we can talk 90, 45, give me increments of that. Don't, whatever. Okay, so I'm going to do the same thing I did last time. I'm going to use my whole graph. I'm going to label 2 pi. However, I'm not going to write 2 pi because we're going to talk degrees this time. So what is 2 pi in degrees? 360. What did I miss? He typed the wrong answer. 720 would be 4 pi. Thank you for participating, though, at least. Okay.
I was like 720, yeah.
I honestly couldn't tell what it was. I could just tell that it was unfortunately wrong, but okay. Okay, everyone's interested right now, right? Okay, so if this is 360, this is normally 2 pi, right? Once around the circle is 2 pi, 360. Normally I would then do pi. Instead of pi, though, I'm going to put 180. Are you guys with me on what I'm doing here? And then normally I put my halves. What goes halfway in between 0 and 180? 90. And between 180 and 360? Okay. Now, the key is we're going to move this right 20. Again, I don't care for this. Honestly, what I've just kind of been doing, okay, so if this is 0 to 90, Jack mentioned it's a little less than a third, right? So I've just been kind of eyeballing. In other words, I'm not getting specific here, but I'm labeling. I'm labeling that 20 degrees. What is 20 degrees more than 90? 110. So I'm going to label 110. What is 20 degrees more than 180? 200. 20 degrees more than 270? 290. And 20 degrees more than 360. It's not ideal, but it's the best I got. Okay, this was secant, so that means I am starting off by sketching the graph of cosine. Oh, dang it, I still forgot. I didn't put my 1 or negative 1 in. Did you guys put yours in? Of course we did, Mrs. Sargent. So normally I would start at 0, 1. Instead, I'm going to start at 0, 20. How's that? Normally I would cut through 90. Instead, I'm cutting through 110. Normally I would have a minimum under 180. Now my min is under 200. Normally I would cut through 270. Cutting through 290. Normally I would have a max above 360. Now it's above 380. Does that work for you guys?
Your ones are so much higher than mine. So I'm like,
I don't feel like I got my 20s moved over far enough, but then again. And then what do we do? Asymptotes where? 110 and 290. And then flip your curves. If you want to draw the whole curves out here on the end ones, you can.
this is my favorite part.
Because it's easy part, or because it means you know you're about done with that graph then?
It's like, okay, we're wrapping it up, and there really is no critical thinking to that part. Unless you get the part before that wrong, then it might look bad.
Even the asymptotes, I always feel like, okay, draw those in, flip, okay, we're good, we're there.
Yeah, it's super.
Okay, guys, so I don't know if you guys caught the theme today, but we've been working on reciprocal functions. We started with what? Sine and graphed cosecant. We tangent and cotangent, secant and cosine. We've been graphing all these reciprocals. So we're going to culminate here with sketching a reciprocal. Sketch a reciprocal function of the function shown in the right, shown in the figure. So we have a line, and we're going to sketch the reciprocal of this.
Does that mean what? Never mind.
So I'm going to list 3 key points, some of which are already familiar to you.
Write them down anyway.
Okay. I mean, some of these, the first one, you guys know this. You just have to, I don't know if you think about these others we've been doing. The best one to probably explain this to would probably be looking at tangent and cotangent. What happened, and I'm just looking back here for a moment, when we went from tangent, which was given here, to cotangent, what happened to our zeros and asymptotes? They flipped, yes? If it was a 0, it now became an asymptote. If it was an asymptote, it now became a 0. That is true of any reciprocal functions. If you have a 0, so an x-intercept, that will become an asymptote. If you have an asymptote, that will become an x-intercept. And so my first key point I'm going to write is that zeros trade places with vertical asymptotes. So however you want to write that. That's what I'm writing. I'll go ahead and give you the other 2 points, and then we will use them. Points where either the y value is 1 or -1 will stay. So that point will be the same point on the graph. So that was points where y equals 1 or y equals -1 stay. So whatever that point is on the graph, it It'll be that same point on the graph in the reciprocal function. And point 3. Large positive values will become small positive values, and small positive values will become large positive values. Okay, so let me write it down. I guess when I say, well, okay. So large positive values will become small positive values. Small positive values become large positive values. And I'm using positive as my example. However, the same is true for negative. So in all these places, I could sub in negative. So large negative values become small negative values. Small negative values become large negative values. And again, when we start drawing the graph, I'll explain that one more, what it means there. Okay, we're going to practice with these two graphs. We'll start with the easy one. You guys ready with me? Okay. Zeros and vertical asymptotes switch places. So, first of all, do you notice any asymptotes here? No. So since there's no asymptotes, there's not going to be any zeros on my new graph. Okay. Now, do we have any zeros here? Yes. Where is there a 0? At 2. So that 0 is now going to become a vertical asymptote. So when I draw, I'm just drawing on the same graph here. Okay, that is now going to be a vertical asymptote. There were no asymptotes originally, so there's not going to be any zeros in my graph, which means my graph will never touch the x-axis. Okay. Points where y equals 1 or y equals negative 1 stay. Okay. So this point right there, yes? Is that the only place we have a value of y equals negative 1? And yes, right? So this point right here where I drew the dot, that's going to be part of my new graph. My graph will go through that point. Okay, down. That was the obvious one to see. I'm going to argue we do have a location on the graph where y equals positive 1. Nope, there is. It's over, Wade's estimating 3-1. I would have said closer to 4-1. I don't know, 3.5-1. Somewhere in there, yes? I mean, the key is to trace over where 1 was. I put mine more like 3.5-1. I have it 4 in here now that I look,
It's like
but
almost a 4. If I'm using like the straight edge on my book, it's almost a 4. It's not halfway. Does it matter that much?
considering I just put mine at 3.5, I mean, I'm going to give you some room for error here. Now, if you're going to tell me it's over at 7-1, we have a problem. I mean, I made that outlandish on purpose, though, but you get the point, right? Okay, now, let's put this last part into play. So, basically, large positive values become small positive values, and vice versa, small positive. So, what that's saying is, if your graph was getting bigger, it's now in that section going to be getting smaller. If it was getting smaller, it's now going to be getting bigger. Okay, so, and we know our graph has to cut through right here, yes? To the right of this point, what was my graph doing? It was going positive, it was getting bigger, yes? So now my graph is going to get smaller. And it's going to get smaller and run along the x-axis then. Now, only worry up until the asymptote. Between the asymptote and this point here, what is my graph doing? It's getting smaller. So what's my graph need to do?
Freeze.
It needs to get bigger. And so you guys cannot see, but what I just drew is it's going up along the asymptote there. Sorry, the timing of my... Okay, so did you guys catch what? So here to the right of this, y equals 1 point. It was going bigger, so I made mine go smaller. Between the asymptote and my y equals 1 point, it's getting smaller. So mine went bigger. And because there's an asymptote, we know it's going to run, what's our graph do along an asymptote? Runs along it without ever touching it, right? So can you visualize down here? Now, also notice, my graph was all positive over here, yes? It was always above the x-axis. So where was my reciprocal graph? Always above the x-axis. Now this graph is below the x-axis. So where's my reciprocal graph going to be? Below the x-axis. Right here, between the point and the asymptote. Those are small negative values. So what's my graph going to do? It's going to be large negative values. As I'm going down there, those are going to large negative values, yes? Over here to the left of this dot, my graph is going into large negative values, so instead I'm going to go into small negative values along the x-axis. Only cross the x-axis if you have a 0 telling you to do so.
Are we done with that one?
Mm-hmm. Yes, that one's done. We still have the last example to do, but we're done with that one. Okay.
Last one, like, way worse.
There's just more to it. I mean, the graph, there's more to the graph period, so it takes more to think about the reciprocal. Right. Concept, the key points don't change. So I'm going to work my way through those key points. Like the first key point, zeros and asymptotes trade places. So, what kind of things do you see? Okay, so there currently, can you guys agree with Wade? There currently is an asymptote here? Is that what you're saying? If there's currently an asymptote here, what's that going to mean in my reciprocal graph? It's going to cross the x-axis at y equals 0. Any other asymptotes currently there? No, so this is the only place my graph will ever touch the cross the x-axis. Any zeros that should turn into asymptotes? Can we agree? Do we see 3 zeros?
Yes.
So each of these zeros, I'm going to draw in asymptotes. So I drew in an asymptote at -3, an asymptote at -1, and an asymptote at 2. Okay, my zeros and asymptotes have switched places. Points where y equals 1 or -1 stay. So, what I would do here, kind of think about, okay, and I know the pencil is way too thick to make this work, but it gives you the idea. If I'm laying my pencil along as y equals 1, do you see we're going to touch the graph several times? How many times am I going to touch the graph? 3 times? Those are 3 places where those points are going to stay. I can go ahead and draw those points. So I have 2 here on the parabola. One that is just to the left of that asymptote, to the left of -3. One that is just to the right of the asymptote at 1. And then another one that is just past the asymptote at 2. So those will be points in my new graph. And then if I lay my pencil along y equals -1, do we have some intersections there? Yeah. Actually, I think I'm going to call this one the bottom of that parabola. Yeah. So there's one here at the bottom of that parabola, and there's one over here to the left of that asymptote. Okay. Connect the dots? Kind of. Okay, where am I start? What's happening over here to the right of 2? Okay, this whole thing is positive, so I'm going to be positive, meaning I'm going to be above the x-axis. To the right of, that's not even 3, is it? I don't know what that is. 2 something. To the right of this point, it was going up, so now I need to go, it needs to be going down. In between the point and that asymptote, it was small, so mine needs to be big. Any thoughts on what's going to be happening next? We've got to figure out what happens between the asymptote at 2 and at -1. Uh-huh. Yeah, pretty much. Kind of like the tangent cotangent line is what Wade was describing. Over here to the right of this dot, these values are close to the x-axis, so this part of my graph is going to be away from the x-axis. Over here, in between this point and my point at 0, 0, this is going away from the x-axis, so I'm going to go towards the x-axis. Yes, it's going to connect, which that really should be a curvy connect, and I didn't really succeed there. And then we're cutting through the x-axis at 0. Can you realize what's going to happen? We're going to connect and go up and along the asymptote. If it was close to the x-axis, it's now far away from the x-axis, and vice versa. Okay. What's happening between the next 2 asymptotes? It's a parabola, yep. It's basically flipping the parabola, exactly. Did we flip parabolas when we were doing sine to cosecant? Yeah. You're flipping the parabola there. And to the right of negative, or to the left of -3, running along the vertical asymptote and then running along the x-axis. Did you start to see some of the connections there?
Yeah.
I think the more you practice with them, the more you kind of figure out what starts to happen there. Okay, so much for a bunch of work time. I should have known that would be too good to be true. I thought, oh, we're moving along. We've got all this spare time, and then this took us a while. Yeah. You do have about 5 minutes, though. 6 minutes if you want to get technical.